is um, so we had x and y, and I really don't like the autocorrect. Okay, x and y is equal to at p. Okay, now since we have that, we know that we could take um, some subset of the names from here, uh, an infinite subset, as long as it wasn't the entire set. Um, then we know that we have infinitely many of them still left, right? And that's so the analogy there is just like if I take the natural numbers, say n, all right, and if I take away the multiples of 11, so if I take away this set n such that n is equal to m times 11 for some m, for some m in n, okay, then I've still got I've got all the multiples of 2 that are not multiples of 11. I've got all the multiples of 3 that are not multiples of 11, and so on. So there's still infinitely many counting numbers left in this set. Do you agree with that?
Yep.
Okay, awesome. So similarly, we can take away some set of names. Let's call it uh, uh, some set of names. Call it a capital X. Okay, so from L of I'll write it as at P. So that's the set of all names. And if I take away some X, then I still have infinitely many names, and I can still have a full rich calculus that does all I need it to do. Okay, and that's fine. And so I could model injecting names into the pure row calculus from other name sources by treating those other name sources as mapped onto X. So then what I'll do, so that
So as long as the names that you're injecting were part of L at P, you're fine.
No. What I'm saying is, as long as I get to map onto X, right? So I can. So let's make this even more concrete. So we'll go
through a map, through a map,
right. So therefore I get to just forget about the map. So now what I'll do is I'll inject some set of names which I will call M for moniker. Okay, and then so P of M is the usual row calculus, right? So it's going to be 0 or for y from x p, or x bang q, or p par q, or at x. Okay, and but so let's do it this way, just to be super careful. So
I think it should be star x, but yeah.
Sorry, star x. Yes, sorry. Let's do this. We'll have we're going to say that I'm going to use n here, and I'm going to use n here, and I'll use M here and star X there. And now we'll say that M comma N, oh wow, love you autocorrect, thank you, is either that or that, right? Um, and and X comma Y, enough of that, thank you. It really, really wants that to be capital. Is equal to at P. So let's now be a little bit more efficient in our grammar. And we'll just do it this way. And then this is X. Okay, so do you see what we've just done? We've just injected a supply of names. And we can always give a semantics back to the pure row calculus by mapping that supply of names onto some namespace that we picked out from before. And as long as you didn't have uncountably many of those, you can make that mapping. Does that make sense?
Yeah, I think it does. Yeah.
Okay, cool. Right. So this shows you how to get off the ground. So row calculus is pure, and then you can make it more practical, right? By injecting names that are not the same as just quoted processes, and then you can show that less pure version, which is a little bit closer to row lang, has this nice mapping back down to the pure calculus. So now what could M be? Well, now M can be, the strings, strings are, which is typically written this way. It would be, so A, let's do, like, say A through Z, A through Z, 0 through 9, and maybe some, special symbols like hash, etc. Okay, and then you need at least one of them there. So that's so that would give you all your strings, and then you could add to it the URIs, right? And you could add to it, whatever other sources of names you might want. Okay, so now it starts to look a hell of a lot more like your practical programming language. And that was sort of the whole point of the row calculus, is that we can get we can provide these nice step-by-step mappings from a more a user-friendly programming language down to the row calculus. A similar thing happens with the syntactic construct of select. You can encode select down into the row calculus, even though row calculus doesn't have select. And if you look at the compiler, it does that. Although in the case of our implementation, once we sort of demonstrated a compilation, then we moved most of the semantics over into the tuple space. So because that's more efficient. But the whole point is that, again, it's guided in the step-by-step fashion to a minimal calculus, the characteristics of which we know rather completely. All right. So that's the methodology, and why your question is actually a really good one, because it opens up the methodology. Does that make sense to people? Are people following along? This is kind of the heart of things. It's really, really important to understand this kind of stuff.
Yeah.
Hey,
Sweet.
Greg, it's also kind of at the heart of correct by construction. So you just showed how row lang, for one example, can be derived from, or at least partially from, with the row calculus.
That's exactly right. That is exactly the idea. Was showing how we achieve that, right? And the correct by construction is why that's important. Okay.
So I guess I have a follow-up question or related question to that.
Yes.
So given the context of a blockchain, how does the operational semantics and reduction rules apply to that? So given we have the reduction rule that leads to P is now becoming P prime, and how does this work within the blockchain system, especially the execution of transactions? Is it that we have to wait on one namespace that the transaction is validated, and then after that is done and ensured that this transaction was included, then on the namespace P prime the transaction is executed, or how does it work?
Okay, so that's a very good question. First of all, I want to refer you and all the listeners to mobile processes for programming the blockchain, so that it discusses all of those details and gives the context for that. And in particular, what it gives is why it's reasonable to look at this as a transaction. Pardon me. It just snuck up on me there. So essentially, what you can see, if you think about it a little bit, is think of this as an address in the blockchain that does not yet have a value. And so inside P, when we get to P, that means we've crossed the point at which this has a value. Right? So now this address has a value, and we know that having gotten past this prefix here, this right paren, is when that transaction has been committed. And there are multiple different clients, potentially, a bunch of different clients that are all submitting values, in this case Q, to be bound to that address. So that's so that represents the racing of all the different clients. And now what's going to happen is that every validator is running a copy of this redx. All right. So so processes that can reduce, we refer to them as redx's, or reduction expressions. So every validator is running a copy of every validator that's validating in the namespace that includes X is running a copy of this expression. Now, if they're not validating that namespace, they don't care about this expression. So that's how they can proceed in parallel. But if they are validating that namespace, then they have to run consensus. And the reason they have to run consensus is, in this case, there's only one client, but you could have lots of them, right? You could have X bang Q prime and X bang Q double prime and so on. And so the consensus is on which of these things has a race condition, or wins the race. Sorry, my mistake. Which of these entities wins the race? And they'll run Casper until they come to an agreement. on which of the different clients wins the race. And then at that point, they all agree on the winner of the race. And so they all record a particular value as showing up at the address Y. Does that make sense?
Yes.
Awesome. Okay, there. That's the heart of the semantic interpretation for the blockchain. Very, very simple. Very easy. There's nothing to it. And then the rest of this stuff is all just, you know, bread and butter, right? If you have if P has a red X inside it somewhere, then if you run P in parallel with Q, then that red X still gets to go. And then this just is also structural equivalence, right? So if P is structurally equivalent to P prime and P prime reduces to Q prime, then and Q prime is structurally equivalent to Q, then we also say that P reduces to Q. So so basically what we're insisting is that our semantics respects the structural equivalence that we talked about so many times before. But what I want to do today, and more or less on the fly, is to introduce you to some variants, two different variants of the operational semantics for rho, one of which is mentioned in the paper, and one of which is not mentioned in the paper. Both of them are very interesting, and both of them lead to relationships between the rho calculus and modeling physical dynamics that I believe make the rho calculus more suited for modeling physical phenomena, especially biological phenomena, than both the pi calculus and the ambient calculus. And more generally, I believe that they make it more suitable for modeling physical phenomena in general. And what they do is they take advantage of the reflective or recursive structure of, embodied in the relationship between names and processes. So I'm going to get rid of this one, or I'm going to use this. The first thing I'm going to do is I'm going to talk about a relationship between processes that's reminiscent of the kind of relationship that we experience, that we, intuit when we write down, the idea that antimatter and matter annihilate one another. So this idea that there's a sort of a dual counterpart that annihilates the other is something that we see in physics and is a part of a lot of models of the physical world. It also has plenty of precedence in science fiction. So that's just I just want people to be aware that there's lots and lots of precedent for these kinds of ideas. Sorry about that. I'm trying to plug in my machine before I run out of power here. Okay. All right. So hopefully I've piqued your curiosity with those kinds of comments, and you're ready to absorb the idea that of annihilation. So we're going to say that a process P annihilates a process Q, and I'm going to use a funny symbol, which is drawn from physics. So let me. So we want this one. So we say P annihilates Q if and only if looking for the double-ended double arrow. Does anyone see it? That's weird. Of course, they don't have the double-ended double arrow. Ah, here we are. Okay. Let me add that to favorites so I don't lose it again. Oh, okay, so it's apparently it's there, I just didn't see it. Okay, so suppose, so for all, if for all r such that P reduces to R in some number of steps. Okay, so when I put a star by the arrow, it means 0 or more steps. Sorry, and it's not just P, it's P par Q. So if we run P in parallel with Q, and if that expression after some number of steps reduces to R, then that implies that R reduces to 0. Okay. Wow. Okay. Does everyone follow that relationship? Sorry. Can you guys hear me?
Yeah.
Okay. So does everyone follow the relationship here? So P annihilates Q if when you run them in parallel, if they ever reach any state at all, then that state reaches 0 in some number of steps. So I'm going to assert, and then I'm going to ask you to check your own intuitions about this. I'm going to assert that that means that all paths lead to 0. Do you agree with that assertion?
Or what?
All reduction paths lead to 0.
I feel like R came out of the blue here. But,
oh, that's great. I'm really glad you said that. You're right. It does come out of the blue, and we make it not come out of the blue with this quantifier here. So it says any one at all. If you give me any R that is reachable from P par Q via the reduction relation, so I don't care which one. The only thing I care about is whether or not it's reachable from P par Q. That's why it's not really from out of the blue. It's just
so it's like all the R's that result at some point from P.
That's right. All the R's that result from P par Q. That's right. And if that's the case, if you can give me an R that results from P par Q, then that R results in 0.
This makes sense to me in the same way that like when you drop an apple, the earth moves up a little bit and the apple falls down a lot, and they kind of negate each other and it leads to 0. That's how it intuits in my brain.
I see. Okay, it's an interesting perspective. I think most people don't think of the earth as moving. But I understand where you're coming from. So yes. And anyone else? Glenn, Phil, Kenny, does this make sense?
Yes, this does make sense.
Awesome. Okay, good.
The only thing I think in my head when you say all paths or any path or something quite dramatic as that is then I think of, oh, is there some path that would take some unexpected route but still end up in the same spot? I can't think of anything at the time, but
oh yeah. You can have all kinds of strange loopy paths. Like if P was somehow recursive or Q were recursive, they were both recursive, they might loop all kinds of crazy ways. But this basically what this says is that P par Q is terminating.
And so this also would prevent something like something that gets very, very close to 0 but never actually reaches it, like an infinite number of steps that's
rules
that out.
It rules that out. Okay. It says that P par Q as a red X expression is terminating. Okay.
Wait, sorry. It means it has a terminating path, but it also could potentially loop forever, right?
Nope.
No.
Why is that?
I'm imagining P par Q, which through a few reduction steps reduces to P par Q, but also has one possible reduction that reduces it to itself, but could also reduce to 0.
Yes, right. So the important thing is that P par Q, since you can get to P par Q, that means that P par Q eventually goes to 0 because P par Q is an R.
But it could also eventually, go to P par Q again, right? So I mean, I guess if you're viewing the paths as like a random selection, if every path is going to be selected at some point, but if you are controlling the flow of reductions, I don't see how you could say, okay, there is a path that goes to 0, but there's also a path that sort of loops back around to itself. I'm going to always choose to take the path that loops back around to itself.
I understand what you're saying. Yeah. So if we were unfair in our selection of paths, yes, that's reasonable. I see what you're saying. So
does this mean if P were already 0, so then Q is R?
No, Q is still Q, and Q reduces after some number of steps to R.
Including 0 steps or 1 step?
Including 0 steps, you could make it that, but it doesn't have to be that. It has to. It's just like if there's an R that you can get to after some number of steps, then R goes to 0.
I guess I didn't understand that. What's to the left of all of I missed that. To what's the conditions ahead?
Okay, so you're asking how to parse this.
Yeah.
Okay, so that
part's fine.
Implies
for me.
This.
Yeah.
So the parenthesis is like this.
Yeah. What's the part that's way to the left starting? I'm sorry, I missed that.
Way to the left. So
yeah, that's at the very.
This is a binder for this, and this expression is equivalent to this. So we write whenever we write this, we mean this.
Yeah.
So I'll take even under the more relaxed interpretation that Jake has given, our definitions will still work. So what I'm going to do now is I'm going to modify the semantics by adding a precondition to the left of our workhorse. And I'm going to say that suppose that X is equal to at P and that Y, yes. And let's call this X sub target. Yeah, so let me hit this. And actually, let me use a, wow. Let's try that again. There we go. And then arrange white format and kern baseline subscript. And suppose further that X sub source is equal to, and let me, instead of calling it at P, I'll call it at R and at S. Oh, actually, we'll use T and S. And then suppose that S is, S annihilates T. Then we're going to and I will fix that one. I think it's, I don't remember. Font baseline subscript. Okay. Then we fix this one up, and this should be, that's the target. And this is the source. Okay, so this is our new COM rule. And I want you to notice something, right? You should be complaining. Why should you be complaining?
Well, I think from what I'm seeing right now, are just because we have them communicating across these channels, it doesn't really say anything about the process that gets run on the other side.
Yeah, that we'll address that concern in a second, but that's not the sort of the complaint that ought to jump out at you. There's a complaint that's really, really important, and I'll give you a hint. Notice that that thing, which is this thing, uses that thing. So remember in when we talked about it last time, these two are dependent upon this arrow here. And this is the only one that doesn't have a precondition. So this is what allows this recursion to get off the ground. There's a base case, right? If everything had something to the left of this implies arrow, how would you ground out the recursive definition of this arrow? Does that make sense? Are people following along? This thing is the base case of the recursive definition of the arrow.
Yeah, that makes sense.
Okay, great. So now let's go to our reformulation. Look to this thing now has a precondition, and the precondition includes this, which includes this. So is this really a well-specified operational semantics? Does it actually get off the ground, or is it forever looping? Because if it's forever looping, it's not an interesting operational semantics. And this is why, and exploring this particular variation is, I'm trying to help you understand some of the characteristics of operational semantics. And that's why I wanted to look at this. It turns out to be quite interesting in its own right, but it helps you understand operational semantics.
And just to clarify, Greg, and one of the reasons why we're implementing these things in something like Scala is because even if you didn't intuitively catch that, if you tried
Scala.
to implement this, it wouldn't compile.
That's exactly right. Scala would be like, whoops, sorry, there's no base case here. Haskell would happily do this. And then you try to run something and it would and it would consume all your heap. Or blow your stack. One or the other. Okay. So here's why this gets off the ground. Notice that 0 par 0 is structurally equivalent to 0. So use our triple arrow or triple equals here. Of course, we don't have it in the favorites. See if I can find it here.
It is in the favorites. Last
Oh, it
row.
is? Last row. Oh, there it is. Sorry. Yeah, my eyes are just not working this morning. Okay, is structurally equivalent to 0. Well, that implies that after 0 steps, so let me put that implies that 0 par 0, 0 par 0 goes after 0 steps to 0. Let's see if I can get the fonts to line up here. Everyone agree with that?
Yes.
Okay. And that accounts for all of the R's. There are no other R's. That gives us all the R's. Okay. And so what that means, therefore, we can conclude that so that implies that zero annihilates 0. Yes?
Yep.
Awesome. Okay, good. So therefore, we have that at 0 from at 0, 0, running in parallel with at 0, 0, reduces. Are everyone comfortable with that?
Yes.
Yeah.
Awesome. Okay. Right. So we've shown that we've gotten off the ground, and we've shown an additional thing, because we know that that thing reduces to 0. Agreed? Because if we substitute 0 in 0, if we substitute the code for 0 in the code for 0 in 0, we get 0. And so, since that's the case, we also have been able to show that this thing annihilates this thing. So we have 2 more names that can serve as source and target. And from now we're off to the races. The whole thing, you can build up infinitely many names that reduce. Is that making sense? Or that allow for redexes, that allow for processes to reduce. So you have infinitely many names that serve as one end of the channel and the other end of the channel. So you have both ends of the channels covered, and so now you have processes that communicate. Are you with me?
Yeah.
Okay, good. This is really, really important. And so now let me talk about why this is important in the case of physical phenomena. So in the case of physical phenomena, when we talk about physics, right, and we talk about chemistry and we talk about biology, there's not just an implied, but a very, very explicit reductionist viewpoint, right? So in particular, the dynamics of biology are supposed to be accounted for by chemistry, right? So when we look at biological phenomena, for example, like a cell interacting with food, that happens because the sugar molecules in the food are interacting with the molecules on the surface of the cell. So there are sites which bind to those sugars chemically, and then there are chemical reactions that relate to the digestive process of that cell. Now, if we look at the chemistry, right? The chemistry happens, at least in the Western view of how things operate, because there are physical reactions. There are specifically nuclear reactions. So 2 molecules interact because, for example, they share electrons. And we continue on down, right? So there are those interactions are accounted for because of subatomic interactions. For example, the dynamics of quarks are hypothesized to play a role in the nuclear reactions. And who knows how far down that goes. But in standard model physics, we have further reductions in terms of fields. Now, that's exactly what this does, right? So you'll notice that the operation at this level of scale depends upon an operation at another level of scale. Right? So these things are happening, for example, at the level of biological entities. And those biological entities are happening because of some things that are happening here at the level of chemistry. And those chemical interactions are happening here because there's another set of, because that's reducing, likewise, because there are some names mentioned, and those names are happening at the level of nuclear interactions. So here we have a system that allows for this stacking or layering of interactions, right? So I can compose things, all the way up to the social level, and then the social level down to the individual level down to the level of organs, the organs down to the level of biological processes, the biological processes down to chemistry, right? So that's what this system does. It allows for that kind of composition. And this is fundamentally different than what we see in the pi calculus, and it is fundamentally different than what we see in the lambda calculus. And yet, the whole system coheres using the same sorts of conceptual tools that we built the lambda calculus out of, the pi calculus, and the ordinary row calculus out of. Does that make sense? Are people following along with this idea?
Yeah.
A little bit. I'm having trouble because is the reduction rule, the left arrow in your highlighted term there, are we saying that still has to be sort of the same reduction arrow that we see up on the top line with p par q reduces in some number of steps to r?
Yes.
Because then that seems like when I'm thinking about, defining levels of interaction at one level versus another level, I'm not, I think it would be quite difficult to find the models of reduction that apply at both levels.
But the nice thing is we found one. That's the whole point.
Okay.
Right. So the one that we found is this one. Right. So this arrow happens if and only if x, s, and xt have this relationship.
Yep.
Okay. So that means that s and t potentially reduce. And in fact, they unless they're zero, they have to reduce. So here's an example of an s and a t that do reduce.
Mm-hmm.
Right.
Mm-hmm.
And so at s would be putting an at in front of this 4, and at t would be putting an at in front of this this output expression. Does that make sense?
Yeah.
Okay.
Yeah.
Right. So in this case, what we're saying is, the zero is, wherever you ground, like if physics grounds out, if it grounds out in quarks, or if it grounds out in strings, or wherever it is, that's what the zero is. And then this is the next level up from that, and then s and t maybe many levels above that.
Greg, but this does at least formulate a ground for physics.
It formulates a ground for this. Now, whether or not physics has a ground or anything like that is that's a separate question. But it's this system has a ground, and the reason we insist on a ground is so that we can have these, so we can write this in Scala. You can play all kinds of games with non-well-founded sets and make the ground very, very far away. You could be falling for a long time. But this system proposes a ground so that we can implement it in Scala. So we have about 4 minutes left, and I want to look at one other variant on operational semantics that will help you get a feel for operational semantics, and also addresses this issue of different layers So operating at different levels. And by the way, you know, this is not just a foundational issue when we're talking about the modeling of physical dynamics. This is a very, very practical issue, especially in biology. So to get a sense of how practical this is, the temporal scale of operation in the nucleus of a cell is just sub-second, right? It's not. It's you know. It's you know. Some operations, you know, if you stack them end on end, can take minutes. Whereas the temporal scale of signaling happening in the cytoplasm are like in the femtosecond range. They're very, very far below sub-second. And yet, if you look at the, like, you know, I was talking about the, you know, single cell organisms interacting with a trail of sugar, right? So that sugar is impinging on the surface of the cell, which is causing reactions inside the cytoplasm, which is then causing reactions in the nucleus, which then produces proteins, which, for example, may turn the flagellum of your single-celled creature. So you clearly have a system which is interacting across these vast temporal scales, like orders of magnitude difference in temporal scales. And this presents an enormous problem for the differential equation approach to modeling biological processes. These vast temporal scales are you know, they make the differential equation models very unwieldy, nearly impossible to handle. Now, I'm not saying that we have a clear and crisp relationship between the differential equations and the model that we have on the page here. But what I am saying is that we have a clear and crisp relationship between all the scales. So now I'm going to make it even more wieldy, even more fun, and I'll do this. I'm going to beg the forgiveness of the Casper folks who are already lining up. And it'll just take a couple of seconds here. So if we go back to this page and we make a oops. There we go. Okay, so now I want to I want to mention the idea of a context. I've mentioned it before, but I'll mention it again. And that is wherever we have a zero, we're going to put in a hole. So we're going to have a context K is either a hole where we could put a process, or it's a for context, or it's an output context, or it's a par context. And we're getting rid of this one because it doesn't have any P's in it. And then we can get rid of this. And there, that's our notion of context. This gives us a way to place holes inside processes, or to knock a hole in a process. And now I can talk about the application of a context to a process, which is defined to be K, in which we have put P for the hole. Okay, very simple idea. We just we have these process expressions which have holes in them, and then we can place processes into the holes. Now, there's a beautiful. It turns out that there's this idea of knocking holes into types, like the type for processes, is governed by the notion of a derivative, and I refer to you to Connor McBride's work to take a look at that. It's a lovely, lovely body of work. But now I'm going to define an infinite number of COM rules. Okay, so this is going to be COM sub k, and this rule is almost there. Okay, and here what we do is at k of q. So when we move, when we interact here, we wrap k up in the context, and then we put that for y, the code of that for y. Now, what's the motivation or justification for thinking about things like this? So probably many of you are aware that HTTP is typically written over top of TCP. And in many, many cases, you might have applications that are used to talking to other applications at the TCP level. And you might have applications that are written and are used to talking to each other through HTTP. And you might want to wire them up so that the TCP applications can talk to the HTTP applications. So what you need to do is you need to put an adapter in place that will unpack HTTP requests and turn them into TCP requests, or to package TCP requests and turn them into HTTP requests. So that adapter code, where would you put that? Well, if we wanted to model things, an application talking at TCP to an application talking at HTTP, we could model that with this context K, which is providing that adapter, right? Which is packaging and unpackaging applications requests in terms of adapting between different protocol levels. So one more second here, and then I'll leave you guys to think about this for next week. Notice that if I have a COM k and a COM k prime, so remember there are infinitely many of these rules, then I can define a new rule, which is the composition of the two rules. So I can define a k, let's try it this way. So I can compose k with k prime, right? So I take a rule like this and a rule like this, and what do? Well, how about I just compose the two contexts? There. So now we have the ability to talk about composing two different COM rules. And the reason this is important is because if you look at the literature for providing categorical models of process calculi, one of the clear things that's missing is talking about how you preserve the behavioral structure. So remember, a couple of sessions back, I talked about how classical mathematics, in which I include category theory, rearranges or factors, to use the nomenclature of programming, factors the behavior and the structure differently than the way computer science does. So in mathematics, you have things like monoids and groups and rings and fields and vector spaces and modules and so on. And they all just sit there. They don't do anything. There's no wiggling, there's no action, there's no dynamics until you introduce morphisms. So category theory takes this general view that it inherited from classical mathematics, and it packages things up so that in sort of traditional categorical presentations, the objects are things like monoids, groups, rings, fields, vector spaces, modules, etc. And the dynamics are in the morphisms between those objects. Now, computer science does not do that. It says, I've got my structure like processes, and my dynamics are associated with the thing that encodes, that defines the structure. And that's the operational semantics. And so now when you talk about categories of calculi, like the row calculus or the pi calculus or the lambda calculus, you have to account for the operational semantics, and you have to say how you preserve the operational semantics. And that turns out to be non-trivial, in particular because we have no way to compose operational semantics. I'll let that sink in for a second. There's no way to compose operational semantics. With this COM-K rule, for the first time, we have a way to compose operational semantics. I've given you one operational semantics, I've given you another operational semantics, and now I've shown you how to compose them. And I'll stop there because we're well into Casper time, but looking forward to picking up the conversation next week.
Thank you, Greg. Bye.
Bye. Thank you.
Awesome. Thanks.